The universe may not end the way we thought. That is not a movie line. It is the uncomfortable possibility now hiding inside one of the largest maps of the cosmos ever made. For decades, modern cosmology has rested on a strange but elegant idea. The universe is expanding. Not just expanding, accelerating. Galaxies are moving away from each other faster and faster, driven by something we do not understand. We call it dark energy. And for a long time, the simplest version of the story was this. Dark energy is constant. It does not weaken. It does not grow tired. It does not change its mind. It simply pushes space apart forever. A cold future. A lonely future. A universe where galaxies drift beyond each other's reach. Stars burn out. Black holes evaporate. And everything slowly fades into darkness. That was the map. Then DESI started drawing a better one. And the map began to look less certain. When I first learned about dark energy, I remember feeling strangely disappointed. Not scared. Disappointed. Because the ending of the universe sounded almost too quiet. No final explosion. No dramatic collapse. Just expansion. Distance. Cooling. Silence. The kind of ending where everything does not die all at once, but simply becomes unreachable. I used to think that was the most haunting version of the cosmos, but now, there is a possibility that may be even stranger. What if dark energy is not constant? What if the force pushing the universe apart is changing with time? What if the ending we imagined was based on a number that may not stay the same? Tonight we explore why dark energy may be changing, and why the fate of the universe may be less settled than we thought. The instrument at the center of this story is called DESI. The Dark Energy Spectroscopic Instrument sits on a telescope in Arizona and uses 5,000 robotic eyes to capture the light from galaxies and quasars across the universe. That sounds simple. It is not. Every point of light DESI measures is a timestamp. A galaxy nearby shows us the relatively recent universe. A galaxy billions of light years away shows us the universe when it was younger. So when DESI measures millions of galaxies across distance, it is not just making a map of space, it is making a map of time. And that is what makes this so powerful. Because dark energy cannot be placed in a jar, it cannot be photographed directly, it does not glow, it does not cast a shadow. It reveals itself through what the universe has done. How fast space expanded, how galaxies clustered, how cosmic structure stretched across billions of years. DESI is trying to read that history. Not from one galaxy, not from 1,000, from tens of millions. In 2026, DESI completed its original 5-year survey. It mapped more than 47 million galaxies and quasars, more than expected, more than any previous high-resolution 3D cosmic map. And hidden inside that enormous structure is a question. Has dark energy always behaved the same way? The standard answer was yes. In the simplest model, dark energy is the cosmological constant, a fixed property of space itself. Wherever there is space, there is dark energy. And as the universe expands, there is more space. More space means more dark energy. More dark energy means faster expansion. It is bizarre, but mathematically, it works beautifully. For years, that was the strength of the model. It was simple. It matched many observations. It gave cosmology a clean framework. But science becomes interesting when the clean framework starts to collect dust. DESI's earlier data hinted that dark energy may not be perfectly constant. The hint is not proof. That matters. It is not time to throw away cosmology. It is not time to say Einstein was wrong. It is not time to declare that the universe is broken. But it is enough to make scientists look again. And sometimes in physics, looking again is where revolutions begin. The key idea behind DESI's measurement is something called baryon acoustic oscillations. The name is terrible. The idea is beautiful. In the very early universe, matter and radiation formed waves, pressure waves, like sound waves moving through a hot cosmic plasma. When the universe cooled enough for light to travel freely, those waves left an imprint, a preferred spacing, a kind of ancient ruler built into the distribution of matter. Today, we can still see that ruler in how galaxies are clustered across space. Measure the ruler at different times in cosmic history, and you can track how the universe expanded. That is the trick. DESI uses galaxies as markers. It measures their distances and redshifts. It looks at the large-scale pattern. Then it asks, did the universe expand exactly the way the standard model predicts? And this is where things become uncomfortable. The first years of DESI data, especially when combined with other measurements, suggested that dark energy may have evolved over time. Not wildly, not dramatically, but enough to matter. Enough to raise the possibility that the force shaping the future of the universe is not a fixed background setting. It may be dynamic, changing, weakening, something more complex than a constant. That should not be possible in the simplest version of the model. And that is the point. The universe is not required to be simple. We are the ones who prefer simple equations. For a while, the cosmological constant was comforting because it was clean. One number, one pressure, one smooth explanation for acceleration. But if dark energy changes, then we are not dealing with a simple constant anymore. We may be dealing with a field, a process, a new form of physics, something that evolves across cosmic time, something that was stronger or weaker in the past, something that could alter the far future. Think about what that means. The fate of the universe is not a philosophical question, it is a measurement problem. If dark energy stays constant, the universe likely expands forever. Galaxies vanish beyond horizons. Star formation ends. The cosmos grows colder and emptier. But if dark energy evolves, the ending becomes less certain. Maybe expansion still wins. Maybe acceleration slows. Maybe dark energy weakens enough that gravity begins to matter again on the largest scales. Maybe the universe does not simply fade. Maybe its future has not been written yet. That is not a prediction. It is a crack in certainty. And cracks in certainty are where cosmology becomes alive. Of course, there is another possibility. The hint could disappear. The data could sharpen. The full 5-year DESI analysis could bring dark energy back into line with a cosmological constant. Some hidden systematic error could explain the tension. A calibration issue, a mismatch between datasets, a statistical fluctuation, a subtle assumption buried inside the model. This is why scientists are cautious. They have to be, because the history of astronomy is full of almost revolutions, signals that looked profound, then faded, anomalies that turned into dust, patterns that vanished when better data arrived. The universe has fooled us before, but that does not make the hint meaningless. It makes it worth testing, and this is what separates science from belief. Science does not protect its favorite ideas by ignoring discomfort. It turns better instruments toward the discomfort. DESI is one of those instruments. Euclid is another. The Nancy Grace Roman Space Telescope will join the search. Future surveys will keep measuring the expansion history of the universe with more precision, and piece by piece, the question will narrow. Is dark energy constant, or is it changing? The answer will not just update a number in a textbook. It will change the story of everything, because dark energy is not a small ingredient. It appears to make up most of the energy content of the universe. Most of reality, in a sense, is controlled by something we cannot directly see and do not understand. That sentence should bother us more than it does. We have names for the dark parts of the universe. Dark matter, dark energy. But names are not explanations. Sometimes a name is just a label we put on our ignorance so it feels organized. Dark energy is the biggest label of all. It is the thing accelerating the universe. But what is it? A constant? A field? A vacuum energy? A sign that gravity changes on cosmic scales? A clue that our model is incomplete? We do not know, and that is what makes this moment so important. Not because the old model has failed. It has not. The standard model of cosmology still explains an enormous amount. The cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, the expansion history with remarkable precision. It is one of the most successful maps humans have ever drawn. but a good map can still be incomplete. And the most dangerous mistake in science is not being wrong. It is becoming too comfortable with being almost right. That is where we may be now. Almost right. Close enough to predict the universe with astonishing accuracy, but maybe not close enough to understand its deepest engine. When I think about DESI, I do not picture a telescope simply collecting light. I picture humanity trying to read the wrinkles in space-time, galaxies as ink, distance as grammar, redshift as memory, a map so large that every point on it is both a place and a time. And somewhere inside that map there may be a message. The universe is not behaving exactly the way you thought. Not loudly, not clearly, not yet, but enough to make us pause. That is the strange beauty of cosmology. The biggest revolutions begin as tiny differences. A small mismatch in a graph, a number slightly out of place, a curve that bends when it should stay straight. At human scale, it looks like nothing. At cosmic scale, it can rewrite the end of time. So here is the question I want to leave with you. Which universe would you rather live in? One where dark energy is constant and the future is a slow, certain fade into cold emptiness? Or one where dark energy changes and the fate of everything becomes unknown again? Some people find certainty comforting, even if the ending is bleak. Others would rather live in a universe whose final chapter has not been solved. I want to know which side you are on. Because maybe the most unsettling possibility is not that the universe is expanding forever. Maybe it is that the universe still has a future we have not learned how to predict.